Okay. Hi, guys. So do you have any questions or comments, maybe? I suppose you all saw the things that I posted, the announcement I posted about the upcoming midterm, right? You saw that. Any questions about the midterm or about assignment one or something? No. Okay. So next week, the whole week is we are off, or is it just Monday? Or just Monday? Wait, Monday, yeah, Monday is Thanksgiving, of course, it's important. But then when is this study break?
That's November 2nd.
Oh, okay. So it's pushed back. Okay, good. So we have the next week. Okay, that's very good. All right. So okay. So let's continue then with. So there is one item left in this section, which in this chapter, I still want to talk about. That is, that's about motion in space. Okay, so this is a kind of physical intuition we have. Now we are thinking of these curves actually as defining motion of a particle in 3D, right? So this R of t, t between dA. So this is a path of a particle moving from R of A in space to R of B in this direction, for example. So, of course, this R of t is what's also called the position vector. It's called position vector. It just tells us at each moment in time where this particle is compared to the origin, which is here, for example. Oh, so this is R of t. Right? Now, if we take R dot of t, this is the velocity vector. Right? Velocity. Again, is a vector. But it's also the tangent, gives you the tangent direction to the curve is the same thing. And we also have this R double dot t. So this we did not talk much, but this is acceleration. This is the acceleration. And you remember we discussed T of t. This was the unit tangent vector, which was R dot t divided by its length. This was the unit tangent vector. Okay, so and then we had the n of t, right? Maybe I just write here n of t. So this was called. So this is just t prime of t or t dot of t divided by norm of t dot t. When I write t dot, I'm using Newton's notation, but this really means t prime. Maybe I used before t prime, but it's the same thing. You can put dot or there is also a third notation, which is ddt, right? So you can also do it that. Anyhow, so this is the normal vector or unit normal. And then we defined finally b of t, which is the cross of the two. B of t, which is remember this was tt plus nt, right? This is called binormal. Of course, I mean, it's clear that this is also unit length and is orthogonal to both T and N. So it forms a kind of triple orthogonal or in fact orthonormal system. So this is T, this is N, and here is P. And these three things form a coordinate system at that point, which moves with this particle in space. This is called Frenet system. Okay, so now one of the things we want to do, we want to use some very elementary observations about these things to prove something really big. Well, I think it's big. It's about Kepler's second law. We can immediately prove using this simple ideas. Actually, not all of it, just very simple ideas. So basically, so this next topic is Kepler's second law. Kepler's second law of planetary motion. Planetary motion. At the end of this chapter, actually, in your book, they do a full treatment, to some extent, full treatment of all three Kepler's laws. Let me drive the second one for now, and then we'll see what they can do later on, or if you want to do all of it or not. Okay, so what's the situation? So this is the particle that moves in space. Of course, Newton told us that this is not completely arbitrary because it has to satisfy an equation which is Newton's law of motion, right? So Newton said. So you remember Newton's law of motion, fundamental law of motion. Anyone out there? Well, F equal to ma, right? It's one of the most iconic equations in the world. F equal to ma. So this F is force that makes the particle to move along some path. M is mass, and A is acceleration. So acceleration I just defined to be A equal to the second derivative of R, right? So A is equal to R dot, which is R. That's acceleration. Okay, so now let me recall something that I already introduced some lectures ago. That is angular momentum. Do you remember angular momentum's definition? Anyone remembers the definition of angular momentum? Yeah, what is it?
Magnitude of the cross product.
What is?
The magnitude of the cross product.
Cross product of what with what?
The radius cross the force vector.
Yeah, and it's not magnitude, it's a vector.
Oh.
Yeah, so angular momentum, it's like torque also was a vector, but this is also a vector, it's a different kind. Angular momentum vector. Remember, L, indeed, as we said, is equal to R cross what? Linear momentum, which is mv, p. where v is velocity, right? So this is equal to m r cross r dot, right? Because v, as I erased here, is r dot, right? Okay. So we have this equation, L equal to that, right? Okay, so now let's differentiate this with respect to L, with respect to T. Differentiate with respect to T. So what do we get? We get dl dt equal to ddt of m r cross r dot equal to, well, we are assuming mass of the particle does not change in time. So this is kind of reasonable assumption for classical non-relativistic systems anyhow. So that's m, this is dr dt cross r dot plus r cross dr dot dt, right? That's a Leibniz rule again. So that's equal to m. Well, what is dr dt? Dr dt is just r dot, right? That's just the definition of r dot. So that's r dot cross r dot plus m r cross dr dot dt, which is r dot dot. So it's like this guy cross acceleration. But this term is zero. R dot cross R dot is zero because we know that the vector, if you cross it with itself, you're going to get zero. So this is equal to zero. So that's equal to m r cross r dot. Okay, so the equation that we derive is the following equation. Dl dt is equal to mr cross r double dot, which is acceleration. So that's equal to m r cross. Now, what was f? F is ma, so this is cross f, right? Because this ma is equal to f, right? Force by Newton's law here is equal to that. So I just write it as r cross f. So it just shows that the change of angular momentum in time is given by this vector. Okay. Now, in planetary motions, the force has some particular property. It's always attractive towards the sun, towards the center of the attraction. So, but if F is along R, so such forces are called central forces. It's always called central, i.e., if F is a central force, okay? Well, then what can I say about R cross F? F is along R, right? So then this is zero. So R cross F is equal to zero. And then you really do get something amazing, which is conservation of angular momentum. So we get for central forces, we get a law of conservation of angular momentum. I guess I can adjust this a bit, yeah. Which says the following, of course. It says that, well, dl dt is equal to 0. It's not changing in time. Angular momentum at the initial point of the of this thing, whatever the value it is, it keeps its amount. The vector is constant. So dl dt equal to 0, i.e. L is equal to constant. Of course, it's a constant vector, right? So this is a constant vector. So by this kind of simple manipulations of Newton's equations and the definition of angular momentum, we derive this this law. Now let's see what does it mean in terms of planetary motion. So imagine you're moving in some plane now. Particle moves in a plane. Okay, so this is just in the plane. It's not out. It's not going out of plane. It's not going. It's not a 3D motion. It's a 2D motion. Okay, so we have that. Now it's this one. So this is the vector RT, right? And what can you say about this area? The area over there. So here is RT, here is R of T plus delta T. I mean, the area that this particle sweeps between time T and time T plus T is this whole area, is this, of course, there's a curvy part, but I can approximate it by this triangular area, right? I can approximate by triangular area. So, and the approximation gets better and better if delta T goes to 0. Right? So, now if I want to measure the rate of change of area by time, that picture should tell you that. So let me write it here, area of triangle this area is equal to cross product of these two vectors. This is O, this is R, and this is, so this is R, say magnitude of, in other words, R cross this vector, which is RT plus delta T minus R of T. But is it really this? Or, sorry?
You have to divide by 2.
I have to divide it by 2 because this is really the area of the parallelogram. Right? So I just divide it by 2. That's okay. Divide by 2. That's fine. And if I want to take the rate of change of this quantity with respect to, so area of triangle divided by time, so I can just push this inside, delta t, and then I can take limit as delta t goes to 0. So after taking limit as delta t goes to 0, we get that indeed rate of change of the area swept by the particle. Sweep. Between R time t, this is equal to, this whole thing is equal to length of the following vector. This is equal to length of, or norm of the vector R cross this vector or dot, right? Divided by 2. So this is equal to, well, I can just write it as 1 over n norm of R cross, well, this is V, right? MV divided by 2. So that's equal to 1 over 2m norm of R cross MV. But this is exactly angular momentum. Exactly angular momentum. So we derive that this is equal to 1 over 2m norm of length of angular momentum. This is angular momentum. So now you understand at least one kind of interpretation of angular momentum. Of course, you have a feeling for angular momentum, but now you understand another meaning of this, which is it measures the rate of change of the area that's traversed by the particle at that point. If you just go slowly, I mean, just go instantaneously from t to t plus delta t. So there is a comment here. What is the central force? Oh, yes. Okay, so central force is a force such that F is always along R. So this is R. That's a good question. I mentioned it, but I didn't write. This is R, this is F. So this is central force. The value, the magnitude of this could be anything, but it should be along R at time t. But if it is like this is not central force. This is central force. Got it? Good. Okay, so that's central force, and so that's it. That's the importance of one of the point of that we study angular momentum because of this thing. So then this condition says that so we get Kepler's law. So the consequence is Kepler's second law. Law of planetary motion. So here is an ellipse. Okay. Okay. So sun is at one of the foci of the ellipse. This is sun. And your, say, Earth is here. So it's moving and it sweeps areas as it moves. So what did Kepler say? Kepler said that as Earth moves around the sun, the area that's swept by Earth with respect to this focal point S, which is sun, in equal times, Earth sweeps equal areas. So this is Kepler's area law, also is called. So let me write it. So this is Kepler's area law. In equal times, Earth sweeps equal areas. It's not just about Earth, it is about any particle that moves in space according to the central force. In equal times, Earth sweeps equal areas. And well, this because this rate of change is constant, so in equal times. So in particular, for example, people after Kepler knew that the farther a planet is with respect to Earth, it moves slower because it's just so, if it moves as fast as it's here, it sweeps a larger area, a bigger area. It's not possible. So when it's down here, it should move slower, but when it's here, it should move much faster so that it's able to cover similar areas, equal areas, as it's closer. So when it is closer to the sun, when we are closer to the sun, we are moving faster. When we are farther away from the sun, we are moving slow. Of course, you might say that this is almost obvious because, because we are under the force of gravity of the sun. The farther the force of sun on us is slow. Yeah, but not quite, because this is a very, very quantitative law. It's not just general thing. It's very, very precise law. By the way, I mean, we derived it. I didn't tell you take this as an article of faith. No, we derived it. If you believe in Newton's law, which we have to believe, maybe that's an article of faith. But then this is a consequence. So that's the beauty of this, all of this vector calculus stuff that we did. So you can derive this sort of. Kepler, by the way, did it completely experimentally. I mean, he observed these things, and it took him about 20 years to decipher all the data, because the data was collected by Tycho Brahe, a Danish astronomer before him. So Kepler and Tycho were always at fight with each other. Kepler was a very good mathematician. Tycho was a very good experimentalist. Tycho had collected all this amazing amount of data by observations. He had huge groups of people watching the stars and these planets at night and writing, collecting all the data. But he didn't know what to make of this data. He had amazing data collected, but didn't know how to interpret that. And Kepler knew mathematics. He was a great mathematician, but he didn't have the data. So eventually, apparently, there was a fight between them. So, but luckily for Kepler, Tycho died. Well, some people say that actually Kepler poisoned Tycho in order to get access to his data. So it's an amazing story there. Yeah, I encourage you to read that, this thing between Kepler and Tycho Brahe, by the way. So eventually, the king decided that, okay, because Tycho is dead, he has to give all these books of data to Kepler. He just, okay, this is yours. And he went to seclusion. So he worked for 10 to maybe 20 years, I'm not sure, to decipher these 3 laws at the end of his work. So these are not just, some joke. I mean, it's big time science, really. Did you get my story down there? Maybe you did. Okay. Anyhow, so this was just one application. So, question? So now we are going to next chapter. We are going to talk about a little bit about functions of several variables. Any questions at home? So there is a comment, I guess. Very interesting indeed. Yes, that's an amazing story. I can tell you like 2 hours of a story along those lines, which really what happened. The rivalry between, or competition, or tension, I would say, between Kepler and Tycho Brahe, and each of them were kind of, was very, very different personalities, character-wise also. Tycho was a nobility. He was very calm, kind of grand, but Kepler was always looking for jobs and money and this sort of thing. He had to suffer all his life. So very, very different. Amazing story. Real. Well, that's what we think. You never know. Anyhow, good stories are better than reality. Yeah. All right. So now, this is chapter 4, I guess, right? So we are looking at functions of several variables, 2 and 3 variables. Okay, so up to now, we looked at this sort of vector-valued functions, but these functions were functions of one variable going into a three-dimensional space or two-dimensional space, right? So far, R was a function from, say, R, or like AB, for example, to R2 or R3, right? So this was R of t, right? So this is one variable only. This is just one variable. But now, today, we're looking at functions. We're going to look at functions that depend on two variables or three variables or more even, right? F. We are going to look at functions that goes from some domain, for example, just U inside R2. You know this notation, subset, right? You know this. Subset of R2 now to R2, R3, or R4, you can go, etc. I mean, in reality, your book will be a really, well, let me put R even. In reality, your book doesn't go beyond R, R2 and R3 actually. And also F from U subset of R3, again going to R, R2, R3, etc. So what is this notation now? So this notation is, we just write it as this, f of x and y. X and y belong to U. So this U is called the domain of the function, right? That's the domain that you're given. I mean, the function has to be defined there to start with, right? So this U is the domain of F. So that's an important concept, you can imagine, domain of F. So you should have some mental picture of this situation. And a good mental picture is this. We have this R2, right? We have some domain. It could be anything. I mean, I'm not specifying any particular shape. There's some domain, and you have this function f that takes any point in the domain and gives you a value in the range, right? So it goes into R, for example, one-dimensional, or it can go to R2, and etc. But let's just focus on this first part, going to R. Okay. So so let me give you some examples because this is kind of abstract and maybe too general to appreciate the importance of the concept. So so I would say consider the function of two variables, f of x and y is equal to, well, I mean like x3y plus xy3 plus xy. I mean, obviously, this function is defined for all values of x and y. There's nothing to forbid us to take the value of the function, right? So this is defined for all values of x and y. So define for all x in R and y in R. But if you consider a function which is like a rational function of these two things, if we take f of x and y, for example, equal to 1 over x minus y, right? So this function, its natural domain is we have to delete that line x equal to 1. Right? Is defined only at x different from y, or only for, I would say, x different from y. Because if x is equal to y, you have 1 over 0, and we don't know what to put there. And that's the thing. I mean, so you can see that when you have fractions, for example, places where the denominator is 0 are problems, and when you have a square root, places where under the square root is negative could be problems. Right? So let me just I'll give you an example, another example. So imagine you have this function. Square root of, for example, someone tells you 1 minus x minus y. So the question is, what is the natural domain of this function? What is domain? And by domain, I mean the biggest possible domain, the biggest sort of places, set of points that this can be made sense of. Right? So in that sense. So can you tell me where is the domain of this function?
All numbers except for one, x plus y equals to 1.
All points where?
Except for one, like x plus y equals to 1.
Yes. So this exactly. This should be the set of points such that 1 minus x minus y should be bigger than or equal to 0. That's the only condition, because you're going to extract the square root, and for a square root to be able to define, you need this number. But what is this? This means that x plus y should be less than or equal to 1, right? X plus y should be less than or equal to 1. Now, can you tell me what is the geometry of this set, x plus y less than or equal to 1? Less than or equal to 1, yeah, that's what. Where is, what kind of shape in a space you can draw? X, Y. Okay, here the best thing is to draw the line x plus y equal to 1. That's easy, right? Because that's just a line. So that's just this line. This is 1, and you draw and stop. Now, this line divides the whole space into 2 pieces, actually 3 pieces. Places where x plus y is equal to 1, which is underlined. Here is bigger than 1, and here is smaller than 1. So you're here. You should be here. Okay? So that's the natural domain of this one. So it's good to know this, but it's also good and in fact useful, and sometimes important even, to know this part also, to know the geometry of this equation. Well, it's an inequality, really, right? It's not just an equation, it's an inequality. Anyhow, so your function now is a map that's defined from here to R. Of course, these whole points, all of these points on the line, right? It goes to 0. All these points on the line goes to 0. And well, yeah, I mean, all these lines are going to something constant, actually. So you have a fairly good idea of the nature of this map. On these lines that are parallel to this line x plus y equal to 1, this thing is constant. So that's kind of, there's some nice features of this map. Any question about this? Okay, so finding or identifying the domain of functions is a topic that we need to know because we want to handle all these things. The next thing is that's discussed is the idea of limit of functions. For example, one makes sense of what is limit of f of x and y as xy goes to x0, y0. So now you see how this game is played. There are these concepts in calculus, one-variable calculus, and we take those and we want to find the two-dimensional, three-dimensional analogs of those concepts. We are going by analogy. I mean, we just say, okay, in one variable case, this was the definition. Now, what is the definition in two variable case? So what is this picture? So here, there is this point x0, y0. And so xy approaches x0, y0. This means that you're near this x0, y0. But remember, you can come to this from any direction that you want. From any which direction that you can imagine, you can approach this point. So that is very much unlike the situation on the line where we could approach the point only from two directions, either bigger than point or less than. Here, there's no bigger than, so you can approach in any angle. And actually, you don't have to approach it along straight lines. You can approach along a very curvy line, any which way. Okay, so that's the idea. So so we say this is equal to A if for all epsilon positive, we have absolute value of f of x and y minus A is less than epsilon, provided xy is near x0, y0. I mean, there is a technical definition here, which I don't want to give you. The technical definition, I'll just say it, if there exists a delta such that this is, so let me give you the technical definition, scare you, and then I'll give you the good news that kind of, you would appreciate me after that, after I give you the technical definition. You would appreciate me better, yeah. So if for all epsilon positive, there exists delta positive, so let me write it like this, sorry about that. For all epsilon positive, there exists delta positive such that absolute value of f of xy minus A is less than epsilon if normal of this vector xy minus x0, y0 is less than epsilon. Oh, delta, sorry. So this is radius delta. So conceptually, this is a bit involved, right? Because it tells you that you can make oh, that's epsilon, right. Yeah, backward 3 is epsilon, right? What is that symbol, right? So it's good that my students even answer themselves, so that's very good. There's a communication, internal communication going on, that's good. So you see, this definition is kind of conceptually involved, but what does it say? It says that you can make this value small enough if you get close enough to x0, y0. How close? Well, it depends on epsilon. If you want to make it less than 1/1000, you have to get perhaps closer. So delta has to be much smaller, and so on. Right, so that's the idea of limit. For this concept to be defined, it's not necessary that f be defined at x0, y0. So that's like a usual calculus. So I just put a note here that f need not be defined, or need not defined, at x0, y0. Only on a neighborhood of x0, y0. Just should be defined in a neighborhood of x0, y0. That's a kind of concept. Of course, by neighborhood, we mean exactly all points that are close enough, for example, are of a distance delta to x0, y0. Again, this concept. So now, so there are some situations where we know that the limits exist and it's what you expect, and there is no problem. So let me, these are, I call them simple cases where limits exist, and I don't even expect you to prove that limits exist. And easy to calculate. So, for example, imagine you have a situation where you have like a polynomial function. Like, you know, I mean, something like x2y5 minus x3y, just a polynomial. They have no issues. They have the limits always exist for these guys and the value of the function. So these are very tame, nice, well-behaved, homely functions. You love them. They don't give you any trouble in this regard. Right? So limit of f of xy goes to x0, y0 exists, and in fact is equal to the value of the function at that point, as you would expect, right? As you would expect. But the difficulty arises sometimes when you have things like fractions, and you approach the point in different directions and you get different values. So let me give you examples of that. So let's look at this example, for example. So imagine you have a function like f of x and y equal to, I mean, xy over x2 plus y2. So this function, what is the domain of this function, by the way? Here? Can you tell me the domain of this function?
As long as x and y don't equal 0.
Exactly. So basically that means everywhere except the origin, right? Just one point should be missed, should be deleted. So this is the singularity, this is the bad point, and everywhere else this function is defined. There's no problem. Now I ask the question, does this limit exist? Limit of f of x and y as xy goes to 0, 0. Does this limit exist? Okay. I need one more minute. Thank you. You're going to have holiday on Monday, so you forgive me. Okay, so Does this limit exist really or not? So if the limit exists, means that as you get closer and closer to this point, right, these values should get closer and closer to something. But what that thing could be, that's the question, right? I claim the limit does not exist. And so that's a kind of subtle point here. I say the limit does not exist. And the reason is that if you approach this point along this line, you get some value. But if you approach it along the line like bisector x equal to y, you get another value. So the limit cannot exist. For example, it's enough to show two directions along which you are approaching the origin, but you get different values. So on the line, say y equal to 0, of course, I mean, this function is constant, right? I mean, it's 0, right? F of xy equal to f of x and 0, right? Because y is 0, so that's 0. You don't have even to look at the denominator, that's 0, right? So that's fine. So limit fxy along this line is equal to 0, because I mean it's even constant, so it doesn't have to make any effort to approach something. It's already there even before approaching the point. Right? So that's it. But what about along the line x equal to y? Well, then what we have? We have f of xx. But you have to put x equal to y. You get x squared over x squared plus x squared. All they need is constant half. So along this line, you're approaching the value half. It's actually constant half, so it doesn't have a limit. So this is different from 0. So the limit does not exist. Okay, so as a kind of brain teaser for you guys, just a Thanksgiving surprise, I want you to think about the behavior of function as xy approaches 0. Can you imagine that? How does it look like? I want you to imagine for yourself how this function look like near 0. You may go mad. But it's a good madness. I recommend it. Try that. So how this function behaves as you are near 0. Just imagine its profile. So you know what I mean, right? Put these things under the microscope and look. So imagine you are on this surface near x equal to 0. How does it look like? It's a very nice question. Or if you have access to Mathematica or what's it, Maple, I guess you have student Maple, right, for free or whatever. I don't know. Okay. I think like
for undergrad it's different. You have to go through like some other software provided by Western that allows you to access.
But even you can go online, and there are zillions of free online plotters. You can just give the equation and then gives you the plot for free and see it for yourself. But first you have to try it yourself. Don't go to that app. Okay, guys, have a wonderful Thanksgiving and a great weekend. And I see you then. It seems I have to see you on Wednesday, right? Okay, see you on Wednesday. Thank you. Any question? I'll just stop the video and then